Now, this section obviously looks at the cul-de-sac of the classical wave model, the ultraviolet catastrophe. Here's our little model. Now, I've added, in order for them to explain how objects both absorb and emit electromagnetic radiation, I had to come up with this theoretical object called a black body. All right. Now, a black body is, and we will put the definition down, because it's appeared in the marking key of the WAIS in previous exams, so you need to know what the definition of a black body is. But in year 9, you would have looked at a rough matte black surface absorbing incident light. And you talk about its surface that you could look at a cavity that the light gets into, and it basically reflects around inside this cavity until it's entirely absorbed. Okay? So here's an idea of a perfect black body that all incident light is absorbed, okay, and none is reflected. And I think I've just put down the definition of what a black body is. So just in that space to the right of that hollow object, could you just, don't put the box until we've written down the definition, but I'd like us to get this definition down. And I've got to put it in small writing. Yeah, it is. So maybe just give me a second. We need about 5 lines of text. It's oh, no, that's too much. Try again. It is a theoretical body that absorbs and emits all wavelengths of light. That's it. It's not possible to get a perfect black body, but it is a good approximation. Things like stars and black holes. Okay, so let me just tidy that up. A theoretical body that absorbs and emits all electromagnetic radiation. Cool. Got it written down? Can I move on? Yes? Thank you. So, a theoretical body. Oh, by the way, this is not in the course, but we have an equation, Q over T equals A E sigma T object to the 4th power minus T surrounds to the 4th power. This is the Stefan-Boltzmann equation. The emissivity ranges from 0 to 1, where 1 is a perfect black body. And we might have played around with this in year 9. A matte black surface has a number close to 1, and a shiny silver surface has a emissivity close to 0. But again, it's not possible to get a perfect black body. You cannot get it equal to 1. Interestingly, it's T to the 4th power, and so that's the black body curve. That's why as the object gets hotter, the relative intensity just shoots up. It skyrockets up to very, very large amounts because it's proportional to T to the 4th power. Which is why, if we go, let's just move over the page to this question here, okay? So this appeared in last year's WAIS exam, okay? An experiment was conducted. It's actually useless to the question if you look at what they're saying. Is when heated to 200, at room temperature it was dull and grey. At 200 it was dull and grey. When heated to 7 it was red. When heated to 2,500, it was white hot, okay? Describe the colour and the intensity of the tungsten. Describe why it changed as it's heated, okay? Now, again, particles are jiggling faster, and so they're putting out smaller wavelengths of light, which go from red through to visible light. That doesn't really talk about the intensity. So then you have to say a faster jiggle means that they're irradiating power at a greater rate. Hence the intensity goes up. Not the best definition. If I had a mouse, I would be able to sort of drag this guy over. Or maybe I can. Here we go. There's the marking key. Not the best. So let's just have a look. There was two possible solutions. Doesn't really answer, as temperature increases, there are more molecules vibrating at faster speeds, so the intensity of higher frequencies increases. Or you could attempt to explain Wien's law. Wien's law. What was his name? Wilhelm Wien. But Wien's law is not in the syllabus. But this is the definition of Wien's law that states as temperature increases, the peak wavelength decreases. And then they're going, oh, also, by the way, the Stefan Boltzmann law, which is also not in the syllabus. So this is the problem. You've got a very, very complicated topic that's being dulled down to a year 12 level, but then you've got some really, really smart kids that actually know this because they're interested in it and they go off and study it. All right, so they had to have like a basic particle theory explanation and then the two laws that actually describe it. Then, this question here, okay, 2.7 and 3.4. We have to sketch two black body curves, one of a cold object, one of a slightly hotter object. And it was worth 3 marks. Now, don't draw this. What a lot of students did is this. All right? If you start at the y-axis, that's 0 wavelength, that's infinite frequency. So you had to start a little bit further back. So we do our lopsided bell curve like so. Now, here's the thing. For all wavelengths, the hotter object pumps out more. So you have two curves that cannot overlap. And if you've seen the diagrams that I put in the booklet or the applet that we've played with, shows that they don't overlap. So we would need to do something like that, all right? Such that the peak wavelength decreases as the object gets hotter, and also the relative intensity increases. Okay? And so now we have to label it. So the hotter object needs to be the top curve. All right, so it was only worth 3 marks, but there was a lot of areas where students could trip up. If this overlapped here, or if you started at 0, or if you didn't label them, or if your peak wavelengths were at the same spot. So it's a bit of a tricky kind of question to draw these curves in. Okay? See, a lot of people are told or taught that cold objects are mostly emitting infrared, which is true. We are pretty cold objects and we are emitting infrared. And so people think, oh, maybe the cold object should dominate in this region. Maybe they should be larger in this region. Well, no. Your hot object is dominating across all wavelengths that are emitted. Okay? More infrared, more radio waves, more microwaves, more everything. Okay? All right. Then, have I? No, I haven't. Where did I put? Okay. I want to show you also another question that I don't like, but it's important that you don't like it also. So let's open it up. Let's find the 2017 WACE exam. Here we go. Exams. Justin, could you stop that, please? Brilliant. No, it's still going. 2017 exam. Oh, there he is. Look at that. Question 12. 5 marks. Look at this. Describe the characteristics of a black body. Boom. That was the definition that I just got you guys to write down. Use these curves. Explain why light quanta was necessary. Okay? So, a lot of stuff going on there. Okay? Now, so 1 mark was for your definition, 2 marks for describing the curves. So as temperature increased, the peak wavelength shifted, the intensities increased. And then the last 2 marks was about the ultraviolet catastrophe and then theorized that light was emitted in quanta. Now, let me just bring up the solutions to that, which I'll have to bring up. Marking key 2017. What was it? Question 12? Was it? there we go. All right. So, the students needed to explain what a black body was. A theoretical object that emits and absorbs perfectly, blah, 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 blah. As temperature, all right, so the intensity goes up, peak wavelength shifts to shorter. The ultraviolet catastrophe classically predicted large amount of ultraviolet, but it wasn't. It gave rise to the idea of light being emitted in specific amounts or quanta. It's a very dilute response. There were students that went way into the story behind the equipartition model, stated that there was an infinite states and hence infinite frequencies that could be produced. This led to but all it was asking for, the classical model brought forward the ultraviolet catastrophe, hence it gave rise to the idea of light being emitted in specific amounts. But really, the light being emitted was because the equipartition of states assumption was removed, and it said that there must be a finite quanta as to how your particles could jiggle. Because it was Planck who was saying that it must be the jiggling of those particles that are emitting a quanta of light. Yes?
How did it give rise to the idea that light was being emitted in specific amounts?
Well, this is where it gets really, really tricky. This is where Max Planck said, well, let's suppose that there's an n value that is a discrete number. We put it into that equation, and it'll make the curve, the mathematical curve, fit the empirical data. And again, he was expecting that number to end up actually equaling 0. So that's why he came upon it by chance. It was a mathematical cheat, but it actually ended up being really, really important, to the point where Planck's constant appears everywhere in quantum physics. It's everywhere. Schrödinger and Bohr and de Broglie. It's just a very, very important constant. As we will soon learn, it relates the energy of a photon to its frequency. That's what we're going to get to at the end of this lesson. So, again, a very nasty question that's trying to ask a very complicated topic, but with just students answering it in a very simplified way. Okay? So, we'll just leave it there.
Where's the diagram for that question? Where's the diagram?
I don't know, page 8, question 8. Yeah, that's it. Yeah, you got it. All right, guys, I would very much like us to get to the same part that the other... All right, so, guys, here's the notes from my student. He has summarized this quite well, and he's provided some graphs, but I want us to sketch some of these graphs. But obviously, Planck made two key assertions, discrete values of energy that atoms could have, and that they emit and absorb in discrete packets called photons. It'll make more sense as we get through the course. Could we please get down to page number 18, please? Okay. I know, but we are going to look at the photoelectric effect. Now, this is a very, very important experiment that now supports the particle model of light that suggests that light travels in discrete little packets of energy, like a little corpuscle. Now, we're going to let's just save ourselves some room up here. So this is what the photoelectric effect did. What they did is they took light, all right, and they shone this light onto some shiny polished metal. So here's my shiny polished metal, okay? Now what actually happened was there were individual packets. So I'm just going to put these guys in little circles to look at them as little bullets, all right? And a bullet would come down and interact with an electron sitting there in the metal, minding its own business. This electron would then be ejected from the metal, all right, and travel through the circuit. And these ejected electrons were called photoelectrons. The idea is that the light particle had a certain amount of energy, and like a billiard ball colliding with another billiard ball, it smacked into that electron, and now that electron travels through the circuit with some kinetic energy. Okay? Now, they measured, obviously you need to know when the electrons are there, so you need to have a very sensitive ammeter measuring the flow of these photoelectrons through the circuit. Now, these electrons are going to have kinetic energy. All right, because they had work done on them. The light did work on them, and now they have energy and they're moving through the circuit. And so what you can do is over here, we're going to have a cell, in fact, a variable supply of voltage that can try and stop those electrons from moving. All right. So imagine they're all trying to move through the circuit, and we've put a voltage that's trying to push them back. This is V0, Jake Palandri. V0 is known as the stopping voltage. Stopping voltage. Okay? So have a think. With no stopping voltage, you're going to have a certain flow of current measured in, I don't know, microamps. And then as you increase the stopping voltage, your photoelectron current starts to drop. And when it equals 0, you've got the stopping voltage. That's the energy that's stopping the most energetic photoelectrons. Okay? Now don't worry where this circuit goes. We'll just say, let's just say that it goes to Earth. But for now, you could measure the stopping voltage. Okay? So here is two very important experiments. Could we put current on the y-axis and voltage on the x-axis? Okay? So the photoelectric effect was two separate experiments. In the first experiment, they kept the frequency constant. That's pretty easy. You just have one source of light that you shine onto your metal. And what they did is they varied the intensity. So let's just start off with intensity number 1. And I'd like you to draw this curve here. Intensity 1. And it would be stopped by a negative V0, that's your stopping voltage, okay? So just think, with your light, you get a certain amount of current, and as you start increasing your stopping voltage, nothing, nothing, nothing. And then at a certain point, oh, hang on, it's now going backwards. Really, I don't really know the significance of the positive section, but here, it's now, boom, stopped, okay? Now, let's suppose we have a higher intensity. Let's go I2, such that I2 is greater than I1. All right, maybe there's a filter, and we remove the filter or the stop or the aperture. We get more light shining on our metal. Now here's it. The wave model suggested that a higher intensity wave would have more energy and so would have a higher stopping voltage. That's what the wave model would suggest from this experiment. You would expect this. But that is not what is happened, so don't write that. What happened was, it made sense that with a higher intensity you had more current, but then it was stopped by the same stopping voltage. Okay?
Is I intensity?
I is in this one here is intensity.
The other is current.
Correct, measured in amps. Okay? So, the conclusion from this experiment, we've got 2 minutes left, I've got a lot to write, is that no light had any more energy than the stopping voltage. Because remember, if you multiply the charge by the voltage, you've got energy, work done. Okay? So, just multiply through by Q. No packet of light had any more energy than the stopping voltage. All right? So this was a big thing. Then, last experiment, changing your variables. Now, we kept the intensity constant, and we changed the frequency. Okay? So, same graph, current on the y-axis, voltage on the x-axis. Okay? So now, let's suppose we had F1. Let's go blue light. And you get this curve. And we'll call that V01, stopping voltage 1. But now let's have F2 less. Okay, let's say a lesser frequency. So maybe your higher frequency was, say, blue light, which, oh crap, hang on. Is that right? Higher frequency? Yeah. Higher frequency blue light, you get that. Lower frequency, all right, let's change it to red light. Now, don't ask me how they kept the intensity measure. I'm sure they were measuring the amount of energy per square meter, but this is what they got. They got the following. Now, lower frequency, lower. All right, So this was important, that the stopping voltages was directly proportional to the frequency. And if you multiply through by Q, this was saying that energy was proportional to the frequency of the light, okay? Not the intensity. And so the wave model could not explain the photoelectric effect. So a new model, the particle model, or an old model that had been sort of on the side bench for a couple of hundred years, they say, all right, this is what's happening. You've got an individual packet of energy called a photon interacting with an individual electron. If it is a higher frequency, it has more energy, and when that photoelectron is ejected from the metal, it has more energy because it came from a photon of light that had a higher frequency, higher energy. We will stop it there, but I need you to have an appreciation of these two curves and the significance that it has. Wave model can't explain these two experiments, or one. The particle model does explain this. Okay? Thank you, gentlemen. I'll stop the recording. If you desperately want to see me regard